Here we are for day 8. We're making some progress. We got ourselves off of the North Pole. We arrived in some green little island here. After, I guess, pulling our bags out of some magical airport. Our bag of holding, I guess, since bags apparently are some sort of multi-dimensional space. Multi-dimensional? Extra dimensional? Some sort of magic bag. Bags that can contain bags that can contain bags. And we ended up, finding out that our bag could contain a total of 18,000 bags. That's quite the bag. We did have the shiny gold one. What was the reasoning behind that? Aviation regulations? Bags must be color-coded and must contain specific quantities of other color-coded bags. All because of aviation regulations. I guess maybe if you had enough bags contained in other bags, if one of them did contain some sort of, I don't know, magical elf bomb, it'd have to blow up something like, 18,000 bags to get through. Makes sense. Protection through recursion. Let's see. I'm ready for day 8, right? No. I do need a text file here. To get ready for my text input, name this day 08. There we go. Now I'm ready. We don't have to put too much work into setting up each of these solvers. This AOC helper library I'm using makes everything a lot easier. I got it set up so each time I run it, it'll always run the last, I guess, instance of base day. I haven't looked at it, but I assume it's using some sort of class reflection. All right. 5 seconds. We'll jump in here. Okay. Flight to the airlines reached cruising altitude. Oh. Are we actually taking out now? You narrow problem code to a strange infinite loop in the boot code. Boot code is represented as text file with 1 instruction per line. Oh, interesting. Its instructions contain an operation, ACC, jump, or no op, and an argument. A signed integer like +4 or -20. ACC increases or decreases a single global value called the accumulator by the value given. Jump jumps to a new instruction relative to itself. No op stands for no operation. Okay, so consider this program. Let's go ahead and jump into it and start parsing this. So we should have an instruction and a digit. Oops. So we're going to take each line. Let's go ahead and use regex. Do we need regex? Not really. We could just split on the space. Let's see, so we want, what do we want? We want a list. We're gonna have the code and then the value. Can I do this? Can I use dynamic tuples? Apparently I can. Let's see, so we already have our code here. We just got to extract the value. Make this a long, just in case. Let's see. So value 1 should be our digit. Then we're going to take the first character, if it's a plus, we'll make our we want a substring of this number. We're going to start at 1 instead of 0, so that will grab and on this one we'll give it a minus sign. All right, and then our inputs, we will add our tuple, which I think I can add it like this. So val 0 should be our opcode string, and then val should be our value. All right, let's run through that, see what we get. All right, so our input looks like no op 0, ACC 1, jump -3. All right, looking good. So that part's done. We have parsed input. So what do we need to do with this? So they said this adds or subtracts, does operations against an accumulator. These instructions are visited in this order: no op 1, ACC plus 1, 2. What is this? First, the no op 0 does nothing, then the accumulator is increased from 0 to 1, ACC plus 1. And jump 4 sets the next instruction to the other ACC plus 1. Jump 4, ACC plus 1. Okay. This is an infinite loop. With this sequence of jumps, the program will run forever. The moment the program tries to run an instruction a second time, you know it'll never terminate. Immediately before the program would run an instruction a second time, the value in the accumulator is 5. Okay. So let's also make a hash set of indexes. So we'll use this hash set to keep track of all the codes that we ran. So for this, we want to get our test input value of 5. So we're going to start index 0. So we're going to run until we encounter a run code we've seen before. Why aren't you letting me access run codes? Oh, because we called it ran codes. So while we don't have the current one, so let's how are we going to do this? All right, then we need to execute our opcode. Let's see, so our current code is going to be, let's change this to codes. All right, so if we're ACC, we want to add or subtract. Since that code is already a negative or positive, we can just add. So we say accumulator equals the value of our current code. All right, so that's ACC. If it's no op, we're not going to do anything. We don't really need to check for that one. The other one we do need to check for is jump. And if we come across jump, then we need to set our current index to 1 less than the jump value, right? So jump says +4, and that's this one. 1, 2, 3, 4. So it should be the current index plus the jump value. I think I want -1. Let's make this an integer. We want -1 because when we flip across, we're going to add one more. What do we get for that? Where did we say long? There we go. Oh, we were doing an integer parse anyway. We got a 0, so that's not right. So we come across the first code, which is no op. So we should just be skipping, right? Oh, it quit. Because we already added. Okay. When do we want to add? Here? No. I think this is correct. No, that doesn't make sense. When do we add the current index? Do we check it at the end? So we start at 0. Well, technically we're starting at -1. Let's change this to a do while. So we start at 0. And let's add our current index. So we start at 0 and we add it to our list. But then this would be incorrect. Okay. It's really confusing. All right, let's get our puzzle input and see if we're running this correctly. What do we get for an answer? 17,000? No, 1,700. It helps if you can read. It's a very key skill here. So we got the first one right. Once I learned how counting works. Oh boy. All right. Let's see. You believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be no-op or no-op is supposed to be a jump. No ACC instructions were harmed in the corruption. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. By changing one jump or no-op, you can repair the boot code and make it terminate correctly. Okay. So what we need to do is check. We need to have a validation here that checks whether we can quit. So let's use our test input again here. Replace our puzzle input. And we want to run this. We want to run this non-stop. And we'll only break when we figure out if we can quit or not. So once we get to a code, we need to evaluate whether we can quit or not. And the validation of whether we can quit is if we change a jump or a no-op, will the next iteration be 1 plus the length of codes? Let's see. Accumulator contains a value 8. I guess we also need to check if we're the last to jump. Second to last instruction. If you change the first instruction, the program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file. Either jump is supposed to be no-op or no-op is supposed to be a jump. Attempting to execute an instruction immediately after the last instruction in the file. But this no-op, I mean, it sends you to one more. So I guess for no-op, we need to check whether we're the last no-op or jump in the list. And we can do that I wonder how efficient this is. Is that what I'm supposed to be doing? I guess we want to see if there's any more jumps. Because if there's just another no-op, then we wouldn't have to jump. And then, so this is what we need to do if we come across a jump. Let's see, current index. Count is going to be end minus index. So for the last jump, then we're going to set if we're not the last jump, we're going to continue on as normal. Now, if we come across a no-op, we need to check whether jumping in this place would take us past the end of our set of codes. If current index plus this value is greater than or equal to the end, then we're going to do this. All right, and does that make sense? I think so. Part two. Part two, you've gotten into an infinite loop, didn't you? You certainly did. So let's see. We should have gone 1, 2, 3, 4, 5, and then change this to a no-op. So let's step through this. So this is current index 0, which is, I guess, technically 1. Okay, we jumped to 6, which is this guy. Right? Codes 6 is ACC. Okay, so we jump to this guy. So we should add, go to the next one, and this time we should get what? We should get the jump. So in our jump, we should be checking if we're the last jump. Step into F11. So our collection, our get range collection is 2, jump and ACC. So actually, no, we should be checking a bit further. Get range 6. Okay. Count of 1, so it's just ACC. Current index is 8. It is 9. Okay, so it should have been... what? Like this? So we got the answer 8, which is the correct value. What is the value of the accumulator after this program terminates? Let's go back to our input. See if we can get an answer out of this thing. Ooh, it is definitely thinking. I think we might not have gotten it. So we shouldn't see this thing maxing out our CPU. Why would you not quit? Maybe because we hit the jump thing? Or the no-op thing. Our no-op check may be incorrect. Maybe this should be int -1. Ooh. It is still going nuts. So let's see. We want to check if adding the current index to the jump will take us past the end. So let's see. Let's take this test input again. And let's say that this was a no-op. And this is, I don't know, jump -6. Oh, you know, maybe what they mean for the no-op is that it'll take you past any more jumps. So maybe what we need to do is create a test index. And we'll do this again with our test index. Oh, what am I doing? Here we go. No, we've done something dumb here. So let's go back to where we were. We got an index out of range. All right, so this no op one that we have here, we need to fix this. Hmm. We should have. Hmm. Let's see. Still not giving me a solution. I think our no-op check is here is incorrect. Let's see, I wonder... it's unlikely that we'll find it in here. We have a jump +1 here. We need something that'll take us past 649. Let's see. We get to a no-op. Yeah, we need to check the test jump, not the current index. So it should be this one. Non-negative number required. -8. Test index. Still nothing. I'm pretty sure our jump check is correct, but our no-op check is not. So once we get to a no-op, we want to check if changing it to a jump will get us out of the program. So we take a test index of, this should be current index plus the jump plus 1. Yeah, this is a real shame. I'm like, I was like right at the answer here, and I'm getting all these +1s all over the place. Probably need to take a step back and think about what I'm actually doing here. So let's see. Let's go back to some test input. So if we got, let's say that we got to a no-op. What was the flow for this before? We jumped to 4, which is this ACC. If we got to no-op +2, what would happen? All right, so now we're at so we're at no-op 0. The first one's a no-op? Yeah, apparently so. And then we're on the one that's in position 6. So we're going to take our test index, it says 9. So we got to +2. We're going to jump to what are we jumping to? Our new current index is 7. What? -4. We got the current index 6. What? Six is 2, so we should have got, oh. Seven. Hmm. That is killing me. What is the true exit here? 649? I guess this would be 648. See if we come across this. Dang, is it really just going that slow? That doesn't seem right though. Wonder, wonder how long I should let this run. Maybe that's my problem. Yeah, but unlikely. Not really running a super inefficient process, am I? No, I'm making reasonable jumps. It's not like I'm searching through it. It looks like I'm not coming across anything that takes me past that index. Oh, maybe this is the thing I need to check for as well. Because I guess that would fail my is jump thing. I get a jump at the very end. Ah. Hmm. Are there any items that have both a jump and a negative number? That doesn't seem right. We want to get in this area. Oh. I guess we want a positive number. Well, I guess if we hit that, we got here, we would have got a break regardless. I think this might be our exit, 648. I guess 647. Do we just not get there? Hmm. Oh, maybe it means a jump in any location. Maybe instead of this last jump, we'll do something like this. Hmm. Yeah, I think I completely did this one wrong. So instead of checking last jump, so let's go back to this setup. And then when we get across a no-op or a jump, we don't want to copy the entire list, do we? Let's see, so I mean, if we check will exit and it runs forever, that's not very useful. How do we efficiently check whether we've got to the last? Attempting to execute an instruction. Supposed to terminate. But using exactly one jump or no-op, you can repair the boot code and make it terminate correctly. Exactly one instruction is corrupted. So how do we know? How do we know if we're not corrupted? Does the rule from part 1 still apply? The moment the moment it runs any program command a second time, you know it will never terminate. So we need to do this one again. And then if we get to the condition where it runs another one, we know that we have a infinite running loop. So every time we come by a jump or no op, we want to test solution 1. Let's see, if we get to the point where the current index is the end, then we know that it'll exit properly. Otherwise, it will not exit properly. Okay. Okay, if we want to check a certain index, so if it's a jump, we want to do nothing. Let's see. So we're gonna go through every single one, every single jump or no op, and see if we can flip it and exit properly. Okay, so for no op, if it's a no op or a jump, we want to check now. Let's see. We need our accumulator. Okay. The answer is 9. Really? You know what? Why not? Of course, it's not the right answer. And it's great that it exited. So let's see. What we're doing is if we come across something that's the current index, that is the index we want to check, and it's a no op, then we want to jump. Otherwise, if it's not the index we want to check and it is a jump, we want to jump. Otherwise, we do nothing because it would be a no op. Oh. Should we be... No, because if it was the index we want to check and it was a jump, we would just do nothing. So if we exited properly, we would return true. Otherwise, if we got to the part where we didn't exit, we'd return false. Does this work with this test code? We got 0, so it's not working. Will exit properly. We want to check. We're checking 2. Four. What we really want to check is position 7. So 7 should be our quitter. Oh, we need to blank out the run codes. Okay. Ah, geez. Okay, we're done with that one. Ah, that one killed me. So the big problem with this one was, where is that guy? It's this one right here. The moment the program tries to run any instruction a second time, you know it will never terminate. This was the key rule here that we needed to check. So it wasn't the fact that, you know, if we came across a jump like this, we would know that, you know, changing this to a no op would terminate it, because we can just check the rest of the instructions down the line. But if this was something like, you know, jump negative here and then jump further down and jump over here, you know, various jumps here, check the rest of the code isn't really valid. What you need to do is check the entire execution of it. And the only way you can tell if it's going to exit properly or not is, you know, if you come across 2 codes that have already been ran. Or 1 code that has been ran more than once. So that's what we should have been doing. And, you know, it barely took us any time to get the first one. So really, we just needed to modify this first one just a little bit to have our will properly exit function. It's frustrating. So yeah, we did pretty slow on this one. Well, I mean, it only took 14 minutes to do the first one, and I guess that was even still pretty slow compared to a lot of other people. And then it took me a full hour to kind of, you know, come across that one sentence that I completely forgot about. But that's kind of what happens here. You gotta pay attention to the constraints, learn those rules, and then come across, you know, your valid step-by-step process. That last, you know, how to check if it's gonna loop or not was my problem. But oh well, we got through it. All right, that's it for this one.